Institute for Artificial Intelligence, and he's going to talk about perceptual modeling of sound textures by end-to-end deep learning.
Thank you. Thanks for the invitation. It's a great pleasure, and it's been very interesting so far. I'm thankful to Geoffroy to open the field. There will be some overlap. I'd like to be more specific from the perspective of an electroacoustic composer, maybe looking at the sound textures and also for the methods that I use. I'd like to start out with a short musical example from Bernard Parmigiani, diretto sonoro. It's one of the godfathers of electroacoustic music, acousmatic music. I think you can see that there are note-like gestures in the music, but as well there are materials that are kind of stretched out in time. There are so to say complex materials, and we call them textures. This music is also called sound-based music. So it's the sound materials are not instrumental acoustic notes, but they are materials that are recorded, generated, synthesized, if you will. And this is a very important class of sounds for this electroacoustic music. So the textual sounds are used as malleable sound materials in a kind of fine arts way. So they are kind of sculptured together. And the qualities of these textures are of the spectral quality and also the temporal quality. That is very important. So there's both spectral and temporal qualities that are very characteristic. Usually it's of a stationary nature. This has the advantage that gestural modulations can be superimposed later by the composer. So this is an example of a spectrogram of such a sound texture. You can see that it's actually like a wallpaper. So there's invariance in both in time and frequency. Usually there is a local structure, some statistics of a temporal structure or frequency structure, or stochastic nature, but the characteristics are constant on a larger scale. This comes from the research of Saint-Arnaud, it's really 95. We can also look at the information gain over time. So for pure noise, the saturation of information will be quickly reached. For sound textures, it takes a longer time to actually get a gist of what is happening. But still, it saturates at some point. Contrary to speech or music, where you get some meaning by the time, which actually is a linear increase in information for a long time. The sources of such textures are varied. So there's activity sounds like walking, rubbing, all kinds of different things, and there's machine sounds usually, natural sounds, environmental sounds, animal sounds, or also human utterances that are not of a language-like type. If you listen to a language that you don't understand, with half ear only, that might be like a texture, or children babbling, for example. So usually the electroacoustic composer ends up with this kind of selection of sounds. So it's sort of a snapshot of my Finder. How to find sounds, no? It's the question, like this sound. It's also a quiz, you can guess what the sound is. how to find it there. What is it? What is the name of the sound, so to say? And what are similar sounds in that collection? If I want to use a similar sound, for example, that has a variation of it, I need to know what the sound is like, first of all. The question is how to describe the sound. I will ask you later what it is. So there are two strategies to describe sounds. There's the semantic tagging, which is usually connected to the sound origin, the recording context. So where did I take the sound? What is the object that produced the sound? Is it an instrument? Is it an animal? Is it whatever material? And this is connected to the term of causal listening, coined by Gion. So these would be examples of my collection: a horn file, air, production sound, atmosphere, whatever. Atmosphere is free. And the other strategy is to describe it by inherent sonic qualities, like abstract quality. And this is, of course, useful for describing abstract concepts in sound design, etc. And this is much related to the term of reduced listening. Examples would be a modulated sign, for example. It's an inherent quality, or it's a bouncy quality, or it's a low, long, whatever tone. And of course, as soon as I have come up with a description, and I can parameterize the description, I can also come up with an organization. Because as soon as I have some axis of description, I can do a projection on a map, for example, and lay out the sounds in 2D using various strategies. So component analysis, multidimensional scaling, self-organized feature maps, T-SNE, different ways. These graphs we have seen a lot of times already. John Gray, Stephen McAdams. Question is, how do they relate to the timbre or whatever it is in the textual sound? And there's a problem here. The vertical dimension is something called attack time, or principle the attack of the sound. And of course, in a stationary sound texture, we don't have an attack. Question is, what replaces this axis? Is there something of a quality which replaces this component? Not a nice schematics by Trevor Bishop from this book on sonic art. You can see that the electroacoustic composer likes to think of a sound as an object in time. And there's also a frequency component which is kind of stretched out, so there is no definite pitch, obviously. It's a pitch range, so it's a more complex nature in pitch. And there's another dimension, it's called timbre. It's even branched. You can see that it takes different paths along the time. So this is a very different situation. Obviously, it needs some complex language to describe what the timbre actually is. So in the research that I did, I'd like to, the idea was to look into the description from an ex nihilo approach. So what are the most significant qualities in textual sounds? And we chose to use a technique called Repertory Grid technique. I don't know if you're familiar with it. It's very nice because there's actually hardly any influence by the interviewer other than the selection of the subjects and the items. It has been developed by Kelly in the late 50s, and it's kind of related to semantic differentiation. So the way it works is that subjects are asked to name differences of two randomly chosen items, and they are asked to name adjectives that comprise bipolar qualities. So there's a range spanning from one item to the other. And give an example. So there's actually two different variations. One would be a straight differentiation if the subject is able to name the difference between the two objects. or if it's difficult, there could be a third item taken, and two groups can be formed, and the differences can be so there would be two sounds, for example. And I would ask you as the subject to name the difference in a bipolar way. So, for example, one would say, oh, one sound is of a pitched nature, and the other one is of an unpitched nature. So there would be one quality that would be a listen. It's actually kind of easy for subjects, obviously, to come up with qualities. Usually it works in the way that there are a number of qualities asked for different sound pairs. So in my study I used 10 bipolar constructs per subject, and the subjects then had to rate their qualities they have come up with for 20 different sounds. Fill out a form for that. So these are the sounds, these are the constructs, and they are asked to rate them on a scale of 1 to 5 or 1 to 10, whatever scale you want to use. Of course, the next subject is the same. So one comes up with a great number of qualities. And by going back, so this would form a vector, and this, for example, would also form a vector. And if the vector distance, in a like Euclidean distance, is very close, that would actually say that this is a synonym or synonymical quality. So this is the way how clusters can be found for different subjects or different qualities. This would, for example, be a cluster for high-low. So one person would name the quality high-low, the other one would say it's bright and dull, the other one would say it's dark and bright, or whatever. But by seeing the Euclidean distance in the annotation, you can see that they are all the same. They have the same mean. And the same goes for other qualities like ordered or chaotic, or regular or irregular. It's the same. These are synonyms in the word. So in the end, we've come up with 10 qualities, 10 clusters. And it's actually a semantic field, so you can't easily say that it's exactly the high-low, or exactly bright and dull, or exactly smooth and coarse. So it's a semantic field that is actually opened by those qualities. The original study has been conducted mostly in German, and we have done a translation. And we have subsequently also done an online test, an online forum, where people could participate in rating sounds on these different axes. There were about 200 participants, 17,000 entries into the database. We could actually check that the translation is not an issue. There was a very high correlation of German and English, so to say, annotations in these qualities. So this would be the result for sounds on the axis high and low. So these are all annotations by persons on the online study. You can see that there's a lot of noise, actually, so people do not actually correspond in their annotation. But you can see that some, like the extreme, are more pronounced, so that it's easy to see that the standard deviation is very low here, and the standard deviation is very low on the other extreme. It's higher in the center, actually, of this. I'm sorry that you can't see the standard deviation bars, which are transparent in a way. So we've done an analysis of the agreement, iterated agreement. It's a Klippendorf-Alva measure. It's rather poor, one has to say. So it's not even 0.6. And we have made a cut here, so actually these qualities are not really considered any longer because the agreement is just too poor. We have settled on the above qualities. And you can see that there are some which are actually inherent qualities, like high, low, ordered, chaotic, smooth, coarse, tonal, noisy. Natural, artificial, we cannot easily call an inherent quality. It's a context quality of the sound course, so to say. So this is something which is difficult if you want to come up with descriptors from the signal of the sound without knowing any context. What is also possible, since the agreement is so poor, to make a measurement how many discernible steps are actually possible. So it's more an ordinal scale. It turns out that there are like 5 to 8 steps on the ordinal scale possible that are statistically significant. So for the quality of tonal noise, it would look like this, that the steps are kind of pronounced at the extreme are and less pronounced in the middle. Of course, there's some intercorrelation between the qualities. You can see for some of the axes it's rather pronounced, and for some it's not so pronounced. We could see that there are actually 3 clusters. One stands out, it's high and low. That's kind of independent of the other qualities. Then there is a axis or a field that comprises smooth, coarse, and tonal and noisy, which could be related to pitchness, roughness, I would say. And the other principal dimension would be ordered, chaotic, and homogeneous, heterogeneous, which is basically a temporal thing. So this would relate to some kind of order or predictability, something like this in the sound. There's a temporal quality. So we've also done an analysis of how to relate to MIR audio descriptors. Actually, this was before the publication of the Telecom descriptors. But it's very related. You can see that there is only a high correlation for the quality of high and low. And the other qualities are rather poorly represented by the traditional MIR audio descriptors. So the question is, can we come up with better descriptors that allow us to quantify the experience of the qualities? Since I'm late in time, I will skip a little and go directly to the neural networks. So actually what we have, or what we want to have, is audio descriptors learned from those examples given. So, and the examples are basically pairs of a spectrogram, that is the sound, and the human ratings that we ask to people for different qualities. And what we use is a deep neural network, which models a multivariate regression problem. This is what they do usually. And it looks like this. That on the top you have the spectrogram, and you have various layers. So a convolutional layer, pooling layer, convolution layer, pooling layer, dense layer, and so on. Various layers. And you end up in the 10 qualities that are numbers, basically, by the human ratings. What do the layers do? The convolutional layers are kind of sparse connections between different spatial items, so different parts of the spectrogram. They are 3 by 3. Usually, it's a kind of a small filter kernel, and you have 32 of these filters to encode different qualities within the spectrogram. Then usually there is a nonlinearity. It's not set out on the graph because it's very usual. Then there's a pooling layer which contracts the information, and so on and so on. And there is a dense layer in the lower part which, so to say, correlates all the different spatial parts of the spectrogram. And you end up numbers in that case for a different quality. What is so special about the convolutional neural networks is that they have a lot of parameters to train. So this is a problem because all those layers, you can do the multiplication and you see that there's so and so and so on different elements encoded. And this is an optimization problem that is usually tackled with a method called stochastic gradient descent. And you have to, of course, use measures to regularize your problem so that there is no overfitting involved. And this is done by dropout learning, different strategies to do the optimization process in a way that you don't end up with overfitting. Also, it has been mentioned before, cross-validation is of course a strategy where you only learn parts of your data. Like in this case, it was a 5-fold cross-validation. You learn 80% of the data and you evaluate on the remaining 20%. To be sure that this is actually, you don't just model the spectrum itself, but you can generalize on parts that are not known. And you do this 5 times. So you can also do some introspection. We've seen that there is like this convolution layer in the top. It's after the spectrogram. What is actually coded there? And you can see that it's there's this 32 different convolutions. After this convolution layer, you can see that there are vertical so to say features, and there are more horizontal features here. And there's also some dynamics that is enforced. This is what the convolutions do. So they process basically vertical, horizontal structures and some dynamics. And you can go a layer farther. And doesn't tell you very much, but it's actually interesting that it's very related to this graph we have seen before for the example of the visual texture representation in the cortex, or like regional filtering, cortical filtering. It's very much related to this. And there's also these intercorrelation lines that we have here that are actually provided by the dense layers. So we've come up with some really good measures for modeling the features that we've asked people. It makes a small difference to use the mean of those ratings, or actually confront the network with the individual ratings with the whole statistics. It's not very pronounced. Oops. And this is what the results look like. You can see that there's okay, this is better. So this would be the example for high and low. You can see that there are some sounds which are really nicely modeled by the features, and others that stand out a lot, because probably there are frequency components in there that are of a high and a low nature, and it's not so easy to decide which one is more important. Okay. So to sum up, we have come up with 6 semantic dimensions with a very high inter-rater agreement through our Repertory Grid method. And there are 3 principal axes, something related to pitch, some axis related to pitchness, roughness, and some axis related to regularity on the temporal scale. And presented a supervised machine learning approach for handcrafted descriptors. I've only shown this example with the CNNs. It's superior to the older approach of a heuristic approach to know parameters. And actually what the goal is of such research is to come up with an interface for sound production, basically. You can go to the website and try it out. It's a browser for textual sounds, where the sounds are on a 2-dimensional map, and they are related by their sound qualities. This is actually what a composer likes to have, kind of a palette of sounds. Okay, thanks for your attention.
Thank you. That's very interesting. Can you tell few words about how you obtain the map, actually?
The map, yeah, it's actually the visual representation is a different research project that I didn't touch now. The map is basically if you have 10 dimensions of, or 5 dimensions of descriptions, you have a 5-dimensional space. And here is a projection mechanism. T-SNE is used to map it down to 2 dimensions.
So it's T-SNE.
Yeah, it's a low dimensional to a low dimensional space, and which unrolls the dimensions, so that there are nice neighborhood relationships. And the tile representation of the sounds is a different project, where we have associated each of the 5 qualities that have a high-integrated agreement to some graphical quality. So synesthesia.
Following up upon Jean-Julien's comment previously, I mean, this is kind of a neat question, or might be neat. How would you go about interpreting your convolutional networks in terms of psychological contributions? So say you want to...
I wouldn't do this. No, I mean, the whole nature of the convolutional arithmetic is it's a nonlinear function. So it's very hard to say what the psychological meaning of it is.
So you somehow come up with the audio features that contribute to your high-low dimension, for example.
Well, it's...
If you're interested in the acoustic features, that's
it's possible to make a salience introspection. So if you can actually variate the axis of output and then go back using the gradient, so the kind of reverse gradient, and then see where the output actually changes which part of the input changes the output. And then you can see what actually contributes to the quality of high and low. It is possible to do that. It's kind of tricky, but it can be done. So you can actually see parts of the spectrum, you can highlight parts of the spectrum that are important for the quality. But I would not make any conclusion about the psychological terms. It's basically data in and out. And you have a lot of, the psychology lies in the data. It's very hard to interpret it in this machinery.
Some more questions? Yes?
How did you get to the architecture of the network?
Well, that's a very basic architecture. It's actually a very simple architecture. It only has 380,000 parameters compared to Google, whatever networks that have 1,000 times more.
I mean, why is it 32 3x3 folders and not?
Actually, it's too much. You could reduce it by a factor of 2 for each layer. Each of the kernels encodes a specific quality, like this encoding of horizontal features, vertical features, some dynamic processing. So you need a few filters per layer to actually encode the different variations. I think 16 would be enough probably for this problem. The number of layers is kind of standard. You usually have 2 layers of convolutions and 2 layers of dense representations. The number, the higher the number, the more complex the nonlinear function. So this is the most basic architecture you can actually use to have some results. And we use this very basic architecture to be able to introspect what is happening. The more complex, the more difficult it becomes.
Yes?
Have you tried working with larger filters? Because you only have 2 convolutional layers, and with very small filters, it's giving you very small receptive fields of the neurons.
Yeah, the receptive field also grows by the pooling.
Yeah, sure.
So it's not so small actually. It's I would say about 30 by 30 pins. So it's not so small actually. It's enough to encode the information that you need. Surprisingly, what I was really surprised is that it works for for this quality, which my intuition would be that it encodes some large-scale order or stochastic nature, and actually it doesn't seem to be the case that there's some temporal relationships that are on macroscopic scale. It's more like a microscopic thing, obviously.
Maybe we have time for one last question. Maybe I could ask you a question concerning, you were talking about Shaw, and he translated also Pierre Schaeffer's work on the classification of sounds. I've always been wondering whether we could also maybe use some of his ideas to define new descriptors, like he was talking about iterative sounds, sounds with non-identifiable pitch, or impulsive sounds, and I don't know if you've looked into this work to see if you could find some ideas.
Actually, in the past I have tried to use small spectrum morphology in a way to associate with signal. So signal associated to a system of spectrum morphology. And it turned out that it's a too subjective thing. So actually there's a lot of source bonding connected to it, which is not identifiable by the signal alone. And also the cultural encodings or so are too strong to be really objective about those systematics. The same is with Schaeffer. I mean, the more basic the descriptions, of course, the more likely you find it in the signal. But as soon as they become more musical or whatever, then it becomes more difficult.
Okay, thank you very much.